Students, we're going to introduce what's known as the normal distribution today. In the previous lesson, you learned about uniform density curves, uniform distributions. Uniform is a histogram where the bar heights are all roughly the same, and so we say, well, I knew that was going to happen, and I'm going to draw a rectangle to represent that situation. Well, what is a normal distribution? I want you to think of a normal distribution as an extremely symmetric distribution with a specific set of qualities. So just because a distribution is symmetric doesn't mean it's normal. That is a false statement. But if a distribution is normal, that does always mean that it is symmetric. So a symmetric distribution might be deserving of the nickname normal if certain conditions are met. So, what are these conditions? Well, I'm going to take you to a little website, an applet that I've been using for years, and it's a Plinko board, as you see, and just like on game shows, the balls randomly drop into the top of the wooden pegboard, and it's just pure chaos as to which bin the ball is going to land. But when we look at the behavior of the collective, all of the balls, things actually behave in a very predictable manner. They're forming a normal distribution if you keep track of how many balls fall into each bin. So notice that not only is this roughly symmetric, but it seems to be just extremely, extremely symmetric. I think that this distribution, where these balls are falling, is following a normal distribution. So what does that mean? We're going to go back to the notes and discuss what it means for a distribution to be normal. If you go out and randomly sample many people in a population, body temperatures tend to behave normally. What does that mean? It means that we know that if we measure the body temperatures of thousands of people, that the distribution of their normal temperature is going to be normal. And you've been taught that 98.6 is the only normal temperature. But that's not actually the case. Some people have a higher normal. Some people have a lower normal. My norm seems to be about 97.2. So sometimes when my fever's 98 point something, it actually means that I have a fever. So if your body temperature falls within a certain range of values, this normal distribution would say, yeah, your temperature's just fine. You do not have a fever. If you randomly sample many people of the same gender and age group, all of their heights would be normal. SAT and ACT scores, if you make a histogram of everybody who took the same SAT, you'd see a normal distribution. IQ scores tend to be normal. If you make a histogram of the people who took the same IQ test, turns out that the mean is usually 100. Okay, so what are these special qualities that are required in order for a distribution to be normal? Well, let me bring a picture up. So I'm going to add a picture, and we're going to take a few minutes to look at that picture. It's the same Plinko board that we were looking at just a few minutes ago. So let's take a look at this. Notice that the average is 10.02 and the standard deviation is 2.226 at the moment after 10,397 balls had fallen into the bins. Well, I want you to pay attention to this, and we'll explain it more on the next slide. If I take the mean minus one standard deviation, that's 10.002 minus 2.226. Well, let's see, that's, I'm going to have to grab my actual calculator and get that answer. So let's see what we got here. All right, 10.02 minus 2.226 is 7.794. Okay. Well, let's see. If I take x bar plus 1 standard deviation, that's 10.002 plus 2.226. Well, that is 12.2 something. Okay. Now, I want to show you something peculiar that we know happens. If I go out to 7.7, which, technically means choose all of the bins that are greater than 7.7. So I want you to figure we start right here at this line at 8. And 12.2 doesn't include 13s. So this value is called x bar minus 1 standard deviation, and this value is called x bar plus 1 standard deviation. Well, what's so special about this? If I add up these 4 or 5 percentages, we get 0.12 plus 0.15 plus 0.16, 0.19 plus 0.16, and then we got plus 0.12. So if I was to grab a calculator, 0.12 plus 0.15 plus 0.19 plus 0.16 plus 0.12, I get 74% of the balls fell between those two values. Well, if I had let more balls fall into that bin, it could have changed. Well, what we know about most normal distributions over time is that it's always true that about 68% of the data falls between 1 standard deviation below and above. So we're a little off here, but not too far off. Okay, so let's see. Let's erase that. Now, let's consider, why does it keep deleting my picture? I do not know. Let's just pull it up again. Okay, so let's see here. The next thing I want to show you is x bar minus 2 standard deviations and x bar plus 2 standard deviations. So that's going to be 10.02 minus 2 times 2.226. Well, that's going to be 14-ish. That's going to be 14-ish. Okay? Excuse me. That would be the other answer that I'm about to get. That would be 10 minus 4-ish, and it's 4.4-ish, so that's going to be like 5 point something. X bar plus 2s is going to be 10.02 plus 2 times 2.226, and that's going to be a little bit over 14 point something. Okay, so let's see. If I go out to the 6, because I have to be, 5 point something, so that doesn't include the 5, and then 14 point something only includes the 14s. Well, let's see what happens if I add up all of the percentages from here to here. So if I grab my calculator again, and I have 0.03 plus 0.08 plus 0.12 plus the 0.15 plus the 0.19 plus 0.16 plus 0.12 plus 0.07 plus 0.04, I get 96% of the balls fell into those bins. So 96% of the balls fell between 5 into bins 5 through 14. Okay, so this is x bar minus 2 standard deviations, and this is x bar plus 2 standard deviations. Well, normal distributions over time usually say that about 95% of your data is going to fall between those two values. And then, just to save time, if I took x bar minus 3 standard deviations and x bar plus 3 standard deviations, we would find that collectively probably 100% of the balls fell into those bins. Well, in reality, it's 99.7% of the balls would fall between 3 standard deviations below the mean and 3 standard deviations above the mean. Okay, so when a distribution is normal, these 3 conditions tend to be met, especially if your sample sizing was large enough. This is referred to as the empirical rule of a normal distribution. If a distribution is truly normal, then it will have what's referred to as these empirical truths, sometimes also called the 68-95-99.7 rule. Approximately 68% of the data is within 1 standard deviation below and above the mean. Approximately 95% of the data is within 2 standard deviations above and below in the mean. And approximately 99.7% of the data is between 3 standard deviations below to 3 standard deviations above. So that kind of says that a normal distribution is about 6 standard deviations wide. Okay, so just something to remember there. Now, notice that 99.7% kind of leaves a 0.3% out of the conversation. Well, that's just to say that we would know in most life situations there are bound to be some outliers. About 0.3% of a population tends to be really, really strange high or low values. So, this is what gives any normal distribution its specific shape. Now on this slide, I encourage you to press pause and copy this into your notes or look at this on your handout very, very closely. You need to memorize this. If we say that a normal distribution is supersymmetric and that about 68% of the data falls within 1 standard deviation of the mean, well then notice that we can divide 68 by 2. And we can say that about 34% of the data falls between the mean and 1 standard deviation above, and 34% of the data falls between the mean and 1 standard below. And then 95% of the data falls between 2 standard deviations below and above. Well, that places 13.5s in these 2 slots, so that those 4 numbers add up to 95. And then if we say 99% of data are within 3 standard deviations of the mean, well, then 99.7 falls between this value and this value. So that puts 2.4s into these small areas. And then we've got our room for outliers at 0.1% and 0.1%, weird values. So take a minute to really let this slide sink in and look at it and press pause. And then when you press play again, move on to this slide with me, an actual example of using the empirical rule. And this will be the last slide for this lesson. Use the empirical rule to answer the following questions. A cattle rancher has 10,000 head of cattle. The distribution of their weights is normally distributed, with a mean of 1,100 pounds and a standard deviation of 100 pounds. How can the weights of cattle be normally distributed? Well, if a cattle rancher is doing his job correctly, he's treating all the cattle equally, feeding them, watering them, giving them room to graze and run and stuff like that. Well, then the weights of his cattle should not differ that much. And so he's saying that on average his cattle weigh 1,100 pounds with a standard deviation of 100. So X bar plus S would be 1,100 plus another 100, so that would be 1,200. X bar plus 2S would be 1,100 plus 200, so that would be 1,400. And then if I add another standard deviation to that, this would be, oh Lord, did I make a mistake there? X bar plus 2 standard deviations, would be 1,100 plus 200 is 1,300. and this would be 1,400 pounds. 1,100 minus 100 puts 1,000 as the value. That's one standard deviation below the mean. And then this would be 900, and this would be 800. So the vast majority, almost all of his cattle weigh between 800 and 1,400 pounds. Now, a word about z-scores. We already know that z equals score minus mean over standard deviation, right? So what does that mean? This z-score of the mean in a normal distribution is always 0, because that would be 1,100 minus 1,100 divided by 100. This would be the score that has a z-score of 1, the score with a z-score of 2, and the score with a z-score of 3. Remember, the definition of z-score is the number of standard deviations above and below the mean. So these are the values that have z-scores between -3 and +3. Now, questions that you then answer. What percent of the cattle have weights between 1,000 and 1,200? We add the percentages up between the lines. So that's 68%. What percent of the cattle have weights above 900? Okay, well, let's see. Above 900. Add up all the percentages to the right of this line, or you can add up these two and subtract from 100. So that would be 100 minus 2.5 is 97.5% of his cattle have weights above 900. What percent of the cattle have weights below 1,000? What percent of the cattle have weights below 1,000? Well, let's see here. Below 1,000 is the sum of these three percentages, and you would find that those add up to 16%. How many cows have weights between 900 and 1,200? Now be careful, this says how many. So let's see, 900 is here, 1,200 is here. If I add those up, I get 81.5% of his cattle have weights between 900 and 1,200 pounds. So if I take 0.815 times 10,000, that would scoot that decimal over 4 places, and that would be 8,150 of his cattle have weights between 900 and 1,200 pounds. Would this be important to a cattle rancher to know how many of his cows weigh between 900 and 1,200? Yes, because maybe when you take your cattle to market, the only ones that can be sold are the ones that have those weights. Well, then he knows that he's going to do pretty well if 8,150 of his 10,000 cattle have those weights. Then he knows he's going to have a good day at the market. Okay, I'm going to post these notes, and I'll also post a second homework assignment where you should use the empirical rule to solve problems. Now, in the next lesson, next week when we return, we're going to say what happens if a normal distribution question can't be answered with the empirical rule, and this is an extremely important lesson.